Hey everyone, welcome back. Hope things have been going well for you. Today we are talking about Triton. And no, I'm not talking about strange sea creatures or Greek mythology. I'm talking about a GPU programming language introduced by OpenAI, a way to make our AI models run insanely fast. The first question we have to ask is why? Why do we actually need Triton? What we are looking at right now is a simple graphical representation of an AI system. It mirrors something PyTorch calls a computational graph, a graph that connects a system's inputs to its functions, outputs, and its loss. In this basic example we have two inputs, A and B. They go into a box that takes these values and produces a single output, which we will call C. Then comes the loss, a function that measures how good the system was at predicting C by comparing it against the true value it should have produced. This entire stage from inputs to loss is called the forward pass. Once we know the error, we need to tell the system, hey, A and B, adjust your values so that the function produces a C, the output, that is closer to the ground truth. This is called the backward pass. The error flows backward all the way to A and B, where it's used to correct them. But now imagine to have a really complex function to model. Computing the output could suddenly take very long time if the function is not properly optimized. But why does this problem even exist? At the end of the day, a complex function is really just a collection of building blocks, things like addition, multiplication, or other operations that are already fully optimized inside PyTorch. In other words, every time we use them, PyTorch calls the optimized version of that operation under the hood. So it seems reasonable to assume that stringing together a bunch of already optimized functions will give us one big function that's also optimized overall. Turns out that's not how it works. The problem is that what is actually optimized are the individual functions on their own, but the moment we step out of one of them to move into the next, we hit a massive overhead. And here is exactly why. Each one of these functions is a separate kernel running on the GPU, and none of them talk to each other directly. Every single kernel has to read its input data from the GPU's main memory, do its work, and then write its output all the way back out to the same memory before it's done. So what would actually make the complex function really optimized is if the entire function ran as a single optimized kernel instead of a chain of fragmented ones. And that's exactly what Triton lets us to do. It lets us take all of these individual operations and fuse them into one single unified optimized kernel. This way we can make our network blazing fast. But we are just talking about the forward pass. There is also the backward pass, and there the standard approach might be slower, but it's safe and fully automated. Unfortunately, once we define our kernel, PyTorch sees it as a black box. During the backward pass, we have to tell it how the error should propagate, which means getting our hands dirty with the actual math of deep learning. But don't worry, I will keep things as simple as possible. Plenty of guides on Triton already exist out there. But what I think is missing is a clear picture of what's actually happening in memory while you write Triton code. So today we will start with the hardware fundamentals of the GPU without going too deep, or we would lose the simplicity that makes Triton what is it. Indeed, Triton was created as a simpler alternative to CUDA, which is far more complex, demands much deeper knowledge of the GPU ecosystem, even if is slightly faster. When you want to work at this low level, I think it's better to start simple and move something like CUDA only later, if you want. It's a bit like learning to code, simpler languages first, then C++, then assembly, even through C++ was actually my first language at university. We will then go through 4 examples of turning standard PyTorch code into optimized Triton kernels before wrapping up with a backward pass, the chain rule, derivatives, the real engine behind modern AI that every engineer should understand. But, as always, let's keep it simple. On the PCB, the printed circuit board of a GPU, there is an enormous number of components. What matters to us is the GPU itself on the left and all the little blocks around it. Those blocks are memory chips, DRAM, stacked and wired to the GPU die through a very wide, very fast interface. When we say I have got a GPU with a certain amount of memory, what we mean is that the sum of the capacity of all these individual chips adds up to that amount. So, this virtual sum of all that capacity is what we call VRAM or global memory, shown on the right, and it's a type of DRAM. Now, if we zoom into the GPU chip itself, it's really nothing more than an unbelievably large collection of transistors. But at a logical level, we can break its most important part, the processing cores, down into clusters called graphics processing clusters, or GPCs. Each cluster is made up of a series of blocks called streaming multiprocessors. Inside each streaming multiprocessor, we find warps and a ray tracing core, shown in red. Quick clarification, not every GPU has a ray tracing core. It's a feature found on gaming and visualization GPUs. Pure AI compute-focused data center GPUs actually skip it entirely, since they are not built to render graphics. Either way, it's not something we will actually be using in this series. The ray tracing core is built for a completely different job, real-time rendering, not AI math. The 2 cores we actually care about live inside each warp, a series of CUDA cores shown in green and a tensor core shown in yellow. These are the 2 cores we will be using to make our kernel super fast. The CUDA core is the generalist. It runs one scalar operation, an add, a multiply, a comparison per thread per clock cycle. It's simple and flexible, which makes it perfect for element-wise operations, the same operation applied independently across thousands of values at once. The tensor core is the specialist. Instead of one operation at a time, it's built to run an entire small matrix multiply and accumulate in a single step. That operation sits at the heart of nearly everything in deep learning, every linear layer, every attention block, every convolution, which is exactly why tensor cores are what actually makes modern AI training a difference really fast. The ray tracing core is built for a completely different problem. That's what powers realistic reflections, shadows, and lighting in modern games. It has nothing to do with deep learning math, which is why we won't be using it here. Let's look at a simple example to make what we just discussed even clearer. Suppose you have 3 vectors in VRAM, A, B, and C. We want to perform a simple operation, the Hadamard, or element-wise product, between vectors A and B, and then add the result to C. Let's see exactly where the standard approach differs from Triton's fused kernel philosophy. The graphic below shows a simplified streaming multiprocessor. We are only showing 4 CUDA cores, because that's all we need here. There is also something I haven't mentioned yet, a small memory inside every streaming multiprocessor, where the various cores can store their results. In the standard case, the first operation is the Hadamard, or element-wise product, between A and B. The GigaThread engine, which is a module that schedules the number of threads, create 4 threads. It creates 4 because A and B have a length of 4. Since each CUDA core operates on 2 scalars, 4 threads are enough because each thread is given the exact same recipe, multiply 2 numbers. So, each component of vectors A and B is brought into the shared memory of the streaming multiprocessor. Then, each CUDA core grabs its 2 respective elements, performs the multiplication, and the result is returned to VRAM. This is the crucial step that distinguishes the 2 approaches. The Hadamard operation has its own optimized kernel, but in order to use the optimized kernel for the addition, which is the next operation, it must put the temporary result back to VRAM. Next, the GigaThread engine sees that to perform the addition, it needs 4 threads again. Once again, each thread receives the same recipe, add 2 numbers. So, our temporary result, let's call it x, is brought back into the shared memory along with vector c. The 4 CUDA cores each add their 2 elements and the final result is returned to VRAM. Now, let's look at Triton. Here we use a single fused kernel. Just like before, A and B are thrown into the shared memory, and the 4 CUDA cores perform the element-wise product. But this time, the result stays in the shared memory. Vector C is also brought into the shared memory, and the 4 CUDA cores perform the addition immediately. Only the final result is sent to the VRAM. As you can see, we did everything inside the same streaming multiprocessor. This is the true power of having a fused kernel, avoiding the overhead of moving temporary data back and forth. The L2 cache you see here is designed to buffer this exact overhead in the standard case, allowing us to keep X in the L2 cache instead of VRAM before we do the addition with C. Alright, this video was just an introduction to Triton, a complex technology but highly useful once you understand it well. I hope you enjoyed it, and I will see you in the next video where we will see how to actually write the code to implement the addition of 2 vectors in a single fused kernel. See you soon!